Today we continue our lectures on geometric modeling. As usual, I want to remind you about the website where you can find all course materials. Today's lecture is related to the new course topic on modeling curves and surfaces. This lecture is devoted to shapes of low dimensions, such as curves on a plane and in space, and surfaces defined in the parametric form. This lecture is structured as follows. First, we need to specify a notion of a parametric curve. Then, several practical ways of defining parametric curves will be covered in more details. They include polar coordinates, cylindrical coordinates, and interpolation schemes. Then, we discuss parametric surfaces and their trimmed versions. As you may remember from the first lecture, a shape can be defined by a mapping from a known set. In the case of parametric curves, one-dimensional segment serves as the set A. It is mapped to the desired curve B. In general, parametric curves are defined by mappings of a unit segment to n-dimensional space. Thus, a parametric curve is a one-dimensional shape in n-dimensional space. Parametric equations of a curve are obtained by introducing one more extra variable t, called a parameter, and calculating n-dimensional point coordinates as shown using the functions of the parameter t, which is changing from 0 to 1 on the unit segment of the t-axis. A parametric curve on the plane can be thought as the result of taking a piece of real line, twisting it, stretching it, maybe gluing the ends together and laying it down on the plane. Each component of a point on the planar curve is a function of t, which lies in the parameter interval from 0 to 1 on the real line. Points on the curve are described by a pair of functions of t. As it's shown in the figure, if we are mapping a unit segment, then the point t equals 0 is mapped to the starting point on the curve, and t equal 1 is mapped to the end point of the curve. As t varies, a mapped point moves along the curve. The parameter t can be thought of as the amount of time that has passed as a point moves along the curve. The parameter t can be also a measure of the traveled distance. The simplest object to represent in the parametric form is a straight line and its segment. Let's start from the parametric equations of the straight line going through one given point, x sub 0, y sub 0. They are x equals x sub 0 plus a times t, y equals y sub 0 plus b times t. Note that parameter t is changing here from minus infinity to plus infinity. For the straight line segment connecting two given points, the parametric equations are shown below. X equals x sub 0 plus parenthesis x sub 1 minus x sub 0 parenthesis t. Y equals y sub 0 plus parenthesis y sub 1 minus y sub 0 parenthesis times t. And the parameter is changing from 0 to 1. Let us go through some simple parametric curves and show specific techniques of defining them. The first such curve is a circle. Its parametric equation is shown in the slide. X equals x sub 0 plus r times cosine t. Y equals y sub 0 plus r times sine t. It uses the point x sub 0, y sub 0, which is the circle center, and the radius r. The parameter t is the angle measured from the positive direction of the horizontal axis x, and changing in the interval from 0 to 2 pi. One can ask, how in the world this equation was derived? In fact, the circle and many other curves are more easily described in special coordinate systems, and one of them is the polar coordinate system. The polar coordinate system on a plane is defined by an origin, point O, a semi-infinite line L leading from this point called polar axis. Any point P is represented by a tuple of two components, r and theta. See upper image, where r is non-negative distance from the origin to the point P. Theta is the interval from 0 to 360 degrees. It is the angle between the polar axis and the line from the origin to the point P. In the lower image, two examples of point representation by tuples are shown for points P sub 1 and P sub 2. Whenever we introduce a new coordinate system, the conversion between its coordinates and Cartesian coordinates has to be provided. Here we have the equations for the conversion. From polar to Cartesian coordinates we have upper expression. From Cartesian to polar coordinates we have lower expressions. Two more parametric curves are a spiral and a family of Lissajous curves. From the example of the Archimedes spiral, it can be seen that the polar system makes it more simple to describe some curves. Another famous curve was described by French mathematician Lissajous is better described in Cartesian coordinates. It's attractive to try more adventurous expressions in terms of t in the above equations. The whole idea of the parametric form is that it is easy to generate points on the curve and to bound them to a particular interval of parameter t values. This beautiful curve was designed by Temple-Fay and was called the butterfly curve. Its original description was found in polar coordinate system. To get it in Cartesian coordinate system, one can apply the standard conversion. Superquadratic curves are very popular in computer graphics. They can be given by the shown tricky parametric equations. The key parameter influencing the shape is the power alpha. If alpha equals 1, it is a circle. If alpha greater than 1, it is a kind of star shape with high curvature vertices. If alpha less than 1, it is a curve approaching the rectangle. Now, few examples of three-dimensional parametric curves. Here we can see three-dimensional Viviani curve given by parametric equations of three coordinates x, y, z and shown by its projection and even by 3D animation. To make the design of 3D parametric curves more convenient, there are special coordinate systems in 3D as well. For example, the cylindrical coordinate system is an extension of the polar system into space. A point P in 3D space is represented by a tuple of three components r, theta, and h. R is non-negative. It is the distance from the origin to the point P. Theta is in the following interval, and it is the angle between the polar axis and the line from the origin to the point P. H, height, is the signed distance from xy plane to the point P. Helix is an example of the curve which can be more easily represented in the cylindrical system at the left side than in Cartesian one at the right side. You can also see an example of the protein structure displaying its helix shape with the trick red wire. Curve fitting is a special method for defining new curves using control points. The input data is a discrete set of known points P0, P1, etc. Pk. The problem is to construct new data points, making a curve P at U which closely fits the data points. There are two major types of curves obtained in curve fitting: interpolating and approximating curves. Interpolation is a specific case of curve fitting in which the curve must go exactly through the data points. Approximation curve passes near the data or control points and only endpoints are interpolated. It is an example of data points left and their linear center and smooth right interpolations. The blue curves are different, but they go through the original red points. For the given 2 points, P0 and P1, each coordinate x, y, and z can be linearly interpolated as shown in the upper expression, in the so-called geometric form, as it keeps original geometric points. It can be reformulated in the algebraic form below, which is a polynomial of degree 1 in respect to the parameter u. All u points will be placed on a straight line segment connecting P0 and P1. The above expressions for a line segment can be presented in the shown matrix forms. See the expression U transpose MB in the algebraic matrix form shown below. The same form is used for parametric curves for any polynomial order, just the matrices U transpose M and B change their form and size for each type of curve. Let us introduce the basic 4-point form of a parametric curve segment, and then discuss several specific popular types of parametric spline curves, such as Hermite interpolation curve, Catmull-Rom spline, Bézier spline, B-splines. A spline is a mathematical technique for generating a single curve from pieces. An advantage of breaking a curve into pieces is greater flexibility than you have many points controlling the shape, because changes to one piece of the curve do not have significant effect on remote pieces. To define a spline curve for a range of values for the parameter t, say from 0 to 1, we tie together pieces of curves defined over intervals of values of t. For example, you might assign curve pieces to the three intervals from 0 to 1/3, from 1/3 to 2/3, and from 2/3 to 1. The 4 points in the set of parameters corresponding to the t values 0, 1/3, 2/3, and 1 define the endpoints of the intervals and are called nodes. The minimal order of polynomial which can work with the given 4 points is 3. Therefore, we are looking for the description of the curve in the form of cubic parametric polynomial shown in the slide. 4 equations for each coordinate of x, y, and z are used to determine the coefficients c sub k. For the shown cubic form of the parametric curve segment, given 4 points or nodes allow for constructing 4 linear equations for each of coordinates x, y, z. Solving these 3 linear systems of equations, we obtain 3 cubic expressions, one for each of coordinates of the curve segment. The solution of the above linear system can be represented in the matrix form U transpose MB for a cubic parametric segment PU fitting 4 given points. The main problem with the 4-point form is that it is difficult to join such neighboring segments smoothly with C1 continuity, which means continuous derivatives. The reason is that points or endpoint derivatives of the neighbor segments are not taken into account. Derivatives are necessary to specify tangent vectors for the curves of degree higher than 1. Tangent vectors at the endpoints of curve segments can be used to provide C1 continuity. For a cubic curve represented in the standard matrix form, the first and second derivatives by the parameter u are shown in this slide. Let us see how a curve segment can be defined by 2 points, P0 and P1, and tangent vectors P'0 and P'1 given at these points. Such type of data is usually called Hermite data, and the interpolation scheme is called Hermite interpolation. If we assume a cubic polynomial for the curve description, we can construct the shown system of linear equations for the coefficients of the cubic polynomials for each of coordinates x, y, and z, as shown in the slide. The solution of the above system for the Hermite segment is shown in the matrix form here. A composite Hermite curve is illustrated below. It consists of several Hermite segments, which share endpoints and tangent vectors. Thus, derivative continuity between segments is provided by the Hermite interpolation. The Catmull-Rom spline is a special case of an Hermite curve, in which the tangent vectors at the internal points are automatically generated. For the given 3 points in the image, the tangent vector in the middle point p sub I is defined as a half of the vector connecting the previous point p sub I minus 1 and the following point p sub I plus 1. Such a tangent vector is defined by the shown expression. One of the possible matrix forms for the Catmull-Rom spline is shown for the case of 4 given points. The tangent vectors at the endpoints can be provided by the user or calculated automatically. See the spline segment behavior in the bottom image, where the tangent vector at the point p sub I is a half of the vector p sub I minus 1 and p sub I plus 1. Any changes of the point p sub I position to positions q sub I or r sub I, for example, do not change the tangent vector but change shape of the curve. The Bézier spline is also derived from the Hermite curve. The Bézier form uses 2 additional points to define tangent vectors at the ending points as shown in the right image. A cubic Bézier curve is defined as shown by the beginning and ending points p sub 0 and p sub 3, which are interpolated by the curve, and 2 interior points p sub 1 and p sub 2 used for shape control. The Bézier curve uses auxiliary control points p sub 1 and p sub 2 to define tangent vectors at p sub 0 and p sub 3 respectively, by the expressions shown at the bottom. The standard matrix form for a cubic Bézier curve is given in the slide. A Bézier spline for n control points p sub I is defined by the shown polynomial equation, where b sub I, n at point t are weighting functions called Bernstein polynomials. The plot of the Bernstein polynomials, depending on the index number, are shown at the bottom right. Degree of the polynomials grows with the number of control points. The Bézier curve always passes through the first and the last control points and lies within the convex hull of the control points. Continuity between adjacent segments in a composite Bézier curve can be controlled by the collinearity of the control points on both sides of a shared endpoint of 2 segments, as the image shows. B-spline is a generalization of the Bézier spline defined by the shown polynomial formula, where p sub I are control points and n sub I, p are called blending functions. Any number of points can be added without increasing the degree of the polynomial. The spline is completely local. Changes to a control point only affects the curve in that locality. Closed curves can be created by making the first and last points the same, although continuity will not be maintained automatically. B-splines also lie in the convex hull of the control points. Here we show different requirements to curves and give the types of the curves satisfying different requirements. When we know the desired curve exactly, we can just provide a number of points and ask to interpolate them. An interpolating curve, left, passes through the given control points. Hermite curve and Catmull-Rom spline are in this category. If we want to design a new curve, which passes near given control points, we can ask just to approximate them. Bézier spline and B-spline curves are in this category. Another requirement to a curve is its continuity. In the upper left image, positional discontinuity of a curve is shown, called C0 discontinuity. Such curves are practically useless in computer graphics. In the upper right image, a derivative discontinuity is shown. The curve is not smooth enough because a tangent to it is discontinuous, jumps at the vertex. This is fine for many shapes, but not for a car surface, for example. C1 continuity is provided by all spline curves. The lower left image shows positional and tangential continuity and curvature discontinuity, because the curvature value jumps at the inflection point. Finally, the lower right image shows the most desired positional, tangential, and curvature continuity. C1 continuity related to the first derivative and tangent vectors is provided by Hermite curve, Catmull-Rom spline, and cubic Bézier curve. C2 continuity related to the second derivative and curvature is provided by compound Hermite curve and B-spline. The next requirement is that the curve has to be simple to calculate, because complexity influences computation time. The possible lowest order polynomials for splines are cubic polynomials. One more requirement is local control. If we move one point and the entire curve changes as shown in the lower image, it is called global control. Local control, shown in the upper image, is preferred in computer graphics. It is provided by Catmull-Rom splines, cubic Bézier, and B-splines. Now we go one step up in the shape dimension and we'll discuss parametric surfaces. In general, parametric surfaces are defined by mappings of a unit square to n-dimensional space. Parametric equations of a surface are obtained by introducing two more extra variables, u and v, or parameters, and calculating n-d-point coordinates as functions of these parameters. The mapping is defined by means of the shown parametric equations. A parametric surface can be thought of as the result of taking a piece of a plane, twisting and stretching it, maybe gluing edges of the piece together, and placing it in space. Each coordinate of a point on the surface is a function of u and v, which both lie in the parameter interval from 0 to 1 on the real line. The point u, v lies in the unit square on the uv plane. Points on the surface are described by the three functions shown at the bottom of the slide. The simplest surface is the plane. It can be defined by a point p sub 0 as in the top image, and two vectors q and r. The parametric equation of the plane is shown at the top left. Note that u and v are arbitrary values here, as the plane is infinite. The vector n is orthogonal to the plane and is called a normal. It can be obtained as a cross product of vectors r and q. In the case of the given 3 points as in the bottom image, vectors r and q can be calculated as shown and substituted to the upper equation. There are special coordinate systems making design of surface equations easier. In the spherical coordinates, point P is represented by a tuple of three components, ρ, θ, and theta, illustrated by the diagram. The radius ρ is the distance between the point P and the origin. Phi is the angle between the z-axis and the line from the origin to the point P. Theta is the angle between the positive x-axis and the line from the origin to the point P, projected onto the xy plane. In the spherical coordinates, the equation of a sphere becomes trivial. Ρ is equal to a constant radius r. Parametric equations for a sphere are shown on the slide. The angles phi and theta plays the roles of the parameter u and v here. A spring is a useful parametric surface with the shown equations. Two parameters r1 and r2 influence the shape of the spring cross-section, and the period length parameter defines how many full cycles the spring makes at the unit of its length. The spring at the right has a bigger circle in the cross-section, and it has less full periods per length. A big class of cubic polynomial parametric surfaces is the main tool in the modern design and animation. Any such a surface is defined by the shown equation. We need 16 coefficients for each coordinate component and in total 48 components to determine the specific surface. Typical representatives of this class of surfaces are interpolating surface patch, Bézier patch, and B-spline patch. For example, the interpolating surface patch can be determined by 16 points given in the nodes of the 4x4 grid in the unit UV square. These points allow for constructing 16 equations for coefficients for each of x, y, and z coordinates. This is a well-known object in computer graphics called the Utah Teapot. It is available on the internet as a list of 306 three-dimensional vertices and their indices, defining 32 parametric Bézier patches. A surface may have a boundary where the surface ends. For example, the boundary of a hemisphere would be the circle around the edge as it's shown in the image. A parametric surface with boundary can be trimmed by edges. Edges for the surface are different from those defined by the UV unit square. The edges can not only make an outer boundary, but also holes in the surface. See the image. The boundary edges are defined using trim curves and loops in the unit UV square. Trim loops are defined in the UV square. See the lower part in the image. The loops are mapped to 3D space together with the surface. A left-hand rule is used to specify which part of the surface is removed and which is kept. As you look down on the UV plane while a point moves along the curve, you can hold on to the surface with your left hand. It means that a clockwise loop defines a hole in the surface. See the inner contour in the lower image. A counterclockwise loop keeps the enclosed region and eliminates everything outside, as the unit square boundary in this example. This slide illustrates the basic operation of the boundary construction in solid modeling. Two trimmed surfaces are combined with a sharp edge, as in the upper image, or smoothly, as in the lower image, for making a boundary of a solid object. This is an illustration from a modern solid modeling system, showing many trimmed parametric surfaces with different colors combined into a boundary of some solid. This is consumer product design, a ski helmet. The model is also a boundary glued together with many trimmed surfaces. This is our main textbook where several chapters deal with geometric modeling. Additional references are shown on the next slide. These are references to parametric curves and surfaces used in these lectures.